Hello.
I should introduce you. As you probably know, Charles is going to talk about general relativity.
Yes, I am. So I'm Charles Taylor, as you all know, and today we're going to do a beginner derivation on Einstein's field equation, and underline beginner. Okay, so these papers that we have in front of you, I want to talk about this real quick before we start. I'm going to use an approach followed by Professor Leonard Susskind of Stanford University. He gave a general relativity lecture during 2008, August to December. And it was outlined by Dr. Eagle. He has a PhD in nuclear physics from King's College in London. So I'm going to be following their outline. And so let's go ahead and talk about our agenda first. We're going to do an introduction, brief introduction real quick. I'm going to show you some motivation to why we want to talk about this. And then I'm going to introduce the field equations. And I'm going to tell you what we're going to be doing with them, what we're not going to be doing with them, and just basically give you a kind of outline where we're going to go. And then 2, I want to get to the Metric Tensor. 3, I want to get to the Christoffel Symbols. 4, we're going to talk about curvature, which is going to bring us to the Riemann Tensor, and then to the Ricci Tensor. And then I'll show you real quick how do we get to the curvature scalar. And then 5, we're going to do a real brief overview of the stress energy momentum tensor. We're not going to be able to derive that because we're going to run out of time. And 6, we're going to conclude. So before I start, I do want to ask that this is a timed speech, so I do not have time for questions or comments. So please, if you have a question or comment, write it down, and there will be approximately 20 minutes at the end to discuss these things. Okay? All right. So, also, there's going to be 2 intermissions within the talk. We're going to get a 5-second break because my camera's going to shut off every 30 minutes. So we're going to take a 5-second break. Jake's going to go back, turn it off, turn it back on, and I got a timer up here, so I'm going to watch that. All right, let's talk about the second sheet that you got. If you flip to the second one, notice that these are all equations. And this, you might want to rip this page out if you want, because this is going to be my main thing. I'm going to go to this, we're going to derive each one of these equations, and I'm going to refer to this page a lot. Okay? And then the next pages that you have, you'll notice that those are photocopies from the book. And this talk is a very different way than the book reviews these topics, but I wanted you to know that these topics are in your book, and if you want to dig deeper, you can look in the book, and I highlighted some things for you guys, okay? All right, with all that being said, let's start with the introduction and a little bit of motivation. And it all starts with our good friends Newton, back in the day, right? So Newton was trying to figure out what is gravity. What makes this chalk fall into my hand? Well, back then, he probably didn't have chalk, it was probably an apple or something. So he was like, his first notion was, well, maybe it's an attraction. Maybe, because usually to have a force, I have to apply something. I apply a force, and this table moves. And he was like, but what's the force? There's no hand pushing this down. So he was like, well, maybe this mass is attracted to the bigger mass of the Earth. He's like, maybe there's an attraction going on, right? And we all know his equation, force equals G m over r squared, right? Everybody knows that. Okay, so that was his idea, right? But Einstein said, that's all good, my friend, but this might not work for bigger things when we talk about galaxies and the Earth and the sun. And so he was like, this works well for small things. And he's like, I agree with you, Newton, you're my boy, but we need to find something better. We need to dig deeper. We need to find a better way to talk about this. And so, to understand Einstein's approach, we need to understand 2 things first. One is the principle of equivalence. So the principle of equivalence. So if you've taken any modern physics class, you'll have encountered this. So what this basically means, a brief little thing of this. Let's say I'm in a box, right? And there's me in this box, or you, whoever you want to be in there. And you're accelerating through space at an acceleration g. There's no difference between this scenario and this one where you're on the ground. I'm going to put some grass there so you know you're on the ground. And you're subject to a gravitational acceleration downward. He said there's no difference between these two situations. Okay, so with that being said, we move to the second notion to understand Einstein's approach. And that was that what does light do in these situations? Well, we need to analyze this. So on this side, we're gonna pretend we're flying through space still, right? Let's do this lower. I'm going to shine a light in this box, and it's going to hit here at some time, right? Now let's take another minute in time, or moment in time, and notice the light is traveling that way. Let's do another moment. All right, so when we look at this as a general overview, what's happening in this situation? Light's taking a curved path. And he was like, so light bends in a gravitational field. But remember the principle of equivalence, he said this situation is the same as this situation. So he said if it's happening in this situation, it has to happen in this situation too. So light has to bend in this situation too, but people didn't believe this right off the rip. You know, they were like, come on, man. But this was proven in the early 1900s with a solar eclipse, where the moon blocks out the sun, and we're able to see stuff out in the distance. So this was proven. You know, here's us over here on Earth. And let's say the sun's right here, the moon is like right here blocking out the sun. And we're over here and we're like, oh man, look at this pretty star. I love stars. Stars are awesome. And all the people on Earth were like, this star's so cool. But the astronomers, they weren't dumb. They weren't dumb at all. They were like, no, 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 no. This star, I know this star isn't right here. This star is behind the sun. And since the star is behind the sun, what's happening here is that the mass of the sun is so massive that it bends the space that light travels. And it intersects our view, and so we perceive the star out here. And so that was the first realization that this is true, that light bends in a gravitational field. So no longer is this gravity thought of as an attraction, where Newton was like, here's the sun, and these guys are attracted to each other. And that's why they go around. Oh, by the way, Newton was the one who tied to the same force that brings this down into the same force that brings the moon around. He gave a really clever argument. I'll do it real quick. He said, take me, I'm on this mountain, and this is the Earth. He said, pretend I throw a ball with a certain velocity. It's going to land right there. He said, now pretend I throw another ball with a little faster velocity. Pretend I throw a ball so hard that it goes all the way around and it lands at the back of my mountain. He said, pretend I throw one more where it goes around and it continues to orbit. He was like, so he tied in that the gravity that makes something fall to the ground is the same gravity that brings the moon around the Earth, which is super clever if you think about it. But his idea of attraction wasn't right. So Einstein said, no, 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 no. This isn't what's happening. What's happening is, I'm going to give a poor analogy about what's happening. Let's say this is a trampoline, right? And I put a little marble right here. And it's going to indent that trampoline just a little bit, right? Well, let's say I get on this trampoline and I'm very massive compared to this marble. What happens to this marble? I think we all know it's going to go down, right? He was like, so this is what's actually happening. The sun is so massive that it's bending space-time, and that the Earth is traveling in a straight line in curved space-time, otherwise known as a geodesic. So that's what's happening. So that's the motivation, right? So now I'm going to introduce Einstein's field equations. And I'm going to write it up over here. That way we can always look at it throughout the talk, and we can always refer to it. So Einstein's field equations go as follows. So this is Einstein's field equations. And notice that I'm saying equations because this isn't just one equation. What you're looking at is actually 16 different equations. And, well, actually, there's 10 different equations because 6 of them are actually the same. So what you're looking at right now is 10 different equations. Okay? But what does this stuff mean? You know? Well, first off, the first thing that we're going to get to the metric tensor. And the metric tensor is this term and this term. Okay? So I'll make a note here. Metric tensor. This term right here is what is known as the Ricci tensor. The Ricci tensor. And from the Ricci tensor, we're going to be able to find that we can find the curvature scalar R. R is the curvature scalar. And then finally, you know what 1/2 is. You know what 8 pi is. You know what c to the 4th is. That's the speed of light, right? And we know what g is. Remember, g was from our friend Newton. We don't want to disagree with Newton on small things. We want this equation to fall down to Newton's equation when things are small. Because he didn't want to disagree with Newton because he was kind of right? And then the last term, we got the cosmological constant. I'll tell you a brief little thing about that. And the stress energy momentum tensor. Stress energy momentum tensor T mu nu. So what we're going to be doing with these is we're going to derive the metric tensor, the Ricci tensor. I'm going to show you how to get to the curvature scalar. We're not going to derive this term, but we will talk about it. And basically at the end of this talk, the motivation is that you leave this knowing what Einstein's field equations are. Okay? And so with that being said, let me read off what this equation says though. Because this, when we look at it, we're like, what does this even mean? We got stuff on the left and we got stuff on the right. But if we notice, everything on the left-hand side has to do with curved space and time. Everything on the right-hand side has to do with mass. So remember the analogy of the trampoline that was very poor. What this equation says is mass tells space-time how to curve, and space-time tells mass how to move. Right? Okay, cool. And notice that the analogy that I gave with the light bending, that didn't work because the mass of a photon was 0, and that equation falls apart with that. That's why we needed the principle of equivalence and that stuff to go forward. All right, with that being said, let's dive into the metric tensor and start doing some math, right? All right, so let's say I have a field. It could be any kind of field. It could be an electric field. It could be a magnetic field. But for our purposes, it's going to be a cow field. And there's going to be a cow. Boom. There's our cow. Now, let's say that the cow is some level above space, or above, not space-time, but sea level, right? This is sea level. And the first thing we got to ask ourselves, if we're a farmer, is where's my cow? Where's our cow? Well, to answer that, we need a coordinate system. Right? And now we know where our cow is. It's in terms of x and y. Okay? Now the second thing we need to ask is, when the cow moves, what happens to sea level? Well, it's going to matter what direction he moves, right? Because if he goes, let's say this is like y and this is x. notice that if he goes along the hill, he's not dropping in sea level. But if he goes down the hill, he's going to start dropping in sea level. So we need ways to talk about this. And I'm going to introduce the first concept, a very beginner way to look at this concept, the gradient. And we're going to take a 1 to 10 gradient. Right? This means that for every 10 meters I walk, I'm going to drop 1 meter. Right? For every 10 meters I walk, I drop 1 meter. Now, how do I say this mathematically? Well, mathematically, I'm going to say that the change in sea level is equal to the gradient, how far I walk, that's what I drop, times the amount I actually walk. Now let's do an example real quick so we all just kind of get a feel what I'm going at. Let's say I want to know how far he drops from sea level at 110 gradient times, let's say he walks 5 meters. Okay. What's this? 1/2. So he drops 1/2 of a meter from sea level. That makes sense, right? So we have these two representations for a gradient. Now let's write them over here on the side and we'll continue on. So we have partial phi. I'm just going to take this equation and I'm going to make it in general for x and y. Right? We've got x equals partial phi, partial x dx, partial phi y. Now one thing to note is that these are not the same. These are not the same at all. Okay? So now I'm going to remind you of something that goes back, that we all know and love. And it's Pythagoras Triangle, you know. So the reason for doing this is, let's say our cow isn't the smartest cow, right? And he's not just going to walk in one direction, right? He might walk in a combination of directions. He might walk in a direction that's like that way compared to x and y. So let's analyze this for a sec. Let's say he walks this way. Call that ds. Well, that means that he's going to have a y component and an x component, right? We can all agree on that. So let's analyze our Pythagorean triangle. We all know Pythagoras looks like this. Right? And then let's say we want to add some vectors. We want to add these vectors because these are vectors, and we can do right? And also we can do one more thing. Well, we can take this into our case, right? We can, instead of like ds, let's talk about phi, because that's what we're doing. We're talking about sea level right now. So we're going to do d phi s, d phi x plus d phi y. So that's our case. That's what we're going off of right now. But what is this? And what is this? Well, we wrote these down, right? So let's plug these into this. Yeah. Okay. So now we have our d phi s, which tells us what's going to happen if he walks into a combination of things. So agree with me. I'm going to come over here. So agree that if I change these coordinate systems to, because like I said, we're beginners. So we're looking at 2 dimensions. We're talking about x and y. But let's say we want to broaden our scope just to say, so what I'm going to do is I'm going to take x to x1, and I'm going to take y to y1, or x2. x1, x2, right? So let's rewrite that over here. x1. These should be partials to be more proper. Agree with me that this is the same, right? Okay, now, because we're beginners, we're taking this, but I could continue. So agree, once again, that this can also be written like this. Right? When n is 1, we have our first term. When n is 2, we have our first term. And obviously, we could go on, right? So what you'll notice now, if you get out your equation sheet, we just derived our first equation that we're going to need. 1. We're going to use this equation throughout the talk, and that's the reason for going through this, just so you understand where I'm coming from. Okay. So let's continue on. So anyone that's studied physics at all, or even to be more specific, relativity, right? Meaning special relativity. And what happens in special relativity is there's a problem when we talk about different reference frames, right? Anybody have an idea what I'm talking about? Length contraction, time dilation, things like this, right? So let's say there's a different observer on our hill here, and remember I changed this to x2 and x1, right? So let's say there's a different observer now. We'll call this y1, call this y2. And let's say I want to talk about this coordinate right here. I'm choosing the 1, right? So how do I talk about the y1? In terms of where our cow is, in terms of all the x's. This is very important too, because to talk about the y1, we have to know in terms of all our x's. So in our case, like I said, we're beginners, and we only have 2 to deal with, so that makes it pretty easy, right? So we can drop this down. That's the representation, the projection on x1. And that's the projection on x2, right? But how do we talk about y1 when we know all the gradients of x? So let me write all the gradients of x that we know. I'm assuming that you know all of these, right? Now the question is, how do we get these? Anybody have an idea? No? It's okay, I didn't know either. It's the chain rule, right? So what I'm going to do is, remember I chose y1. So I'm choosing y1. So I'm going to say the partial of phi, partial y1 is equal to, and here comes the chain rule. No, x. Notice, like I said, to talk about y1, we have to know all of our x's. So notice we only have 2 x's to deal with. That's why this one is this, and we're keeping our y1 the same. Cool? All right, but agree with me that I can write this in a more general sense. So agree that this can be written we're going to sum over the m's, because we're not summing the n's. Remember, I choose the nth. I'm choosing the 1. So I'm choosing the nth. So therefore, all the m's are the sum of the x's. Alright? Everybody cool with that? We have, when m equals 1, we have this term. When n equals whatever we choose, this could be 2, 3, 4, 5, 6, 7, we could choose, but we're choosing 1 for n. I think that's important. Cool? All right. And we've just derived our second equation. If you look on your sheet, that is equation number 2. We're going to use 1 and 2 here in about 5 minutes to do something pretty spectacular. So we need to now talk about tensors. Okay? So let's erase some stuff. Okay, tensors. We've all seen tensors before. Obviously in this class you guys have, but for people watching, they might not know what a tensor is right away. So they've all seen tensor, and I promise, because tensor, if we talk about a tensor of rank 0, we're talking about a scalar. An example of a scalar would be temperature or sea level, something like that, right? We'll just use temp, just for now. Temperature of rank 1, or not temperature, tensor of rank 1. Well, this is just a vector, right? And this has 2 special properties. It has magnitude and direction, usually written the other way around, direction and magnitude. Okay, so what I want you to do is, I want you to consider something, like how we transformed our equation 2 from the x frame to the y frame, right? We want to talk about y's in terms of x's. I want you to consider how we do this for vectors now. So how does a vector transform under these conditions? And so I'm going to use equation 1 and 2, if you watch closely and you look at equation 1 and 2, to write equation 3. So we have our sum going on, right? Partial y and n. I believe this is the equation 1 that we're using here. We're saying the phi, for us it's y. So I write the top term like this. I believe this is the x, the m. And then we need something out here. Remember when we were talking about length, it was this dx term, that was a length term, right? So now we're talking about vectors, so we need a vector term right here. X. Remember, we're choosing the nth y, and we're summing over the x's, right? And that's equation 3. If you look at your sheet, we've just derived equation 3. So there's a note now that I should say. Actually, let's take a quick pause and do this here. Everybody take a breath. Need some water.
You take a breath.
All right.
Okay. Go ahead. Good? All right, so what I was about to say is we have to take a note about tensors and why tensors are so important in Einstein's field equations. All these terms have to do with tensors, and it's because tensors have a special property that if there's something in one frame, they have to be the same thing in the other frame. In other words, that they're fixed, right? So they're special in this way, and that's why we like them. And that's going to come into play here in a second. Now I need you to consider something else. I need you to consider what a tensor of rank 2 would be. In other words, a combination of vectors, right? So I'm going to write a combination of vectors. I think I chose N, M. A is a vector. I'm choosing the mth A vector. I didn't give it a frame. Okay? This is a vector. B is a vector. I'm choosing the nth B vector. It doesn't have a frame. But we can write this as TMN, otherwise known as a rank 2 tensor. Okay? So now we're going to use our equation 3, and we're going to write what this would be using this as well. We're going to use this equation and this equation to write our AM, BN in the Y frame. Okay? So we have, I believe it's the Y frame. Yes, it's the Y frame. So we have this. Now I'm going to go to sum. Excuse the sloppy notation, but I don't want to do two sums, so I hope you don't mind that I choose two dummy indices, R and S, summing over those two. And we have partial y m, and we have partial x r, and then we have a m, this should be r, because we're summing over the x's, remember, r and the x. That's the first one, right? That's this first vector. Everybody can see that, right? And then the second one, we have partial y, we're choosing the n, and then we have partial x, s, v, s, x, right? And I can keep going on this, and I can rearrange some stuff, and I can actually do one more thing with these arx, bxs, just as I did out front for this am, bn with the y frame. So that's what I'm going to do next, right? Everybody see that? All I'm doing is rewriting this. I'm putting these two terms at the end, and then I'm substituting for this one more time. AXR BXS is actually TRSX. Everybody see how I got that? TMNY is represented, the tensor, the rank 2 tensor is represented as this. And this is our equation 4. If you look at your sheet. And this also has another name, and this is called the contravariant transformation. Okay? So this is equation 4, and it's the contravariant transformation. But for our case, and for our questions about Einstein's field equations, we're interested in the covariant transformation, not the contravariant. So how do we get the contravariant or the covariant from the contravariant? Well, I'm going to do something pretty silly, but I hope you can follow along because it's not that hard. I'm just going to flip-flop things. So I'm going to flip-flop these. I'm going to flip-flop everything in here, and it's going to give us the covariant transformation. And that's what we need. Okay? So Tmn in the y frame. Notice I'm writing that a little different, but I dropped the mn. We still have this sum going on. And pretty soon here, I'm going to take in Einstein's convention, and I'm going to start dropping sums. But when I do start dropping sums, I'm going to let you all know, just so we are all on the same page. We have partial xr, partial xs, partial y m, partial y n, t, r, s, and the x frame. Right? Remember, we're choosing the mth and the nth term. These are chosen, like we chose the y1, right? We chose the y1, and then we had to sum over all the others. These are dummy indices, but we're summing over the rs. That's the important part to get out of this, is that we're not summing over m and n. These are chosen. Okay? And this is equation 5 that we're going to use a lot, that we've just derived. So if you look at equation 5, it should look just like this, right? Yn, yep. Perfect. So now what we're going to do is we're going to go back to Pythagorean triangle. Pythagoras. We're going to have some fun with my dude. Alright, so what we're going to do is we're going to look at Pythagoras triangle in our new way of looking at it. ds, this was dx1, remember I changed the terms, and this is dx2. So everybody knows Pythagoras, ds squared is dx1 squared plus dx2 squared. And because we're beginners, we're staying there. But I could go on. And agree with me that I can rewrite this. Everyone agree with me, right? Because when we have m equals 1, we have a dx1, we have another dx1, that's dx squared. When m equals 2, we have dx2, we have dx2 squared. And we can continue on. So everybody see how I got that? Alright, good. Now I'm going to complicate things. And you guys are going to like this. Complicate. And what I'm going to do is I'm going to pull a fast one on you real quick. And I'm going to add another indice and I will explain what this is. Basically, I added another sum, but because we can't have a dx1 and a dx2, we have to have a way to kill these terms off. And everybody knows and loves the Kronecker delta. When m equals n, the Kronecker delta is 1. When m doesn't equal n, the Kronecker delta is 0. It kills those terms off, the ones we don't want. Everybody see that?
Should be inside the summation. Otherwise, I would ask, what are m and n?
You're so right. You're so right. This is part of the sum, so it has to be inside the summation. Got a little ahead of myself. Happy? We're all happy now. Good. Okay. So now what I need to do is I need to find representations for these dxm's and these dxn's. And this is where I'm going to call on equation number 1. Right? So let's write equation 1. I want you to remember this. And now I'm going to start dropping summations. Okay? So for equation 1, I want the phi to go to xm, and I want the xn to go to yr. So if we drop the sum and we rewrite equation 1, we will have this. This should be partial dyr without the sum. Right? Alright, so now we have a representation for our xm and our xn term. And now I'm gonna plug this equation in for the m, and then we're gonna switch it for the n. And let's just write that out so everybody is clear about this. These are the two substitutions that I'm gonna make. And I'm going to write these not next to each other, but they're a product, so we can do this. Everybody see what happened? Alright, so now what we've just done is we've stepped upon our first thing that is of importance to us in Einstein's field equation. We've just derived the metric tensor, meaning that this is the summation included. This is GMN. Now you'll wonder, and you'll say, Charles, but that's not G mu nu. And I'll be like, you know what, you're right. But we're beginners, remember? And we're dealing with M and N where we had 2 dimensions. And also, this is space. We're talking about space. Now, mu nu usually takes the values of 1, 2, 3, whereas 0 usually is the time component. And Therefore, mu mu is space and time. Space and time. We've just derived the space component, right? So everybody's happy with that. Good. So we could rewrite the metric tensor, but I think you get the gist. It's this part. So let's talk about flat space now. Let's go back to our Pythagorean triangle. All right, so in flat space, this representation you believe me, right? You totally believe me. You were like, man, I know that. I know that from kindergarten. We all took geometry in kindergarten, right? Okay, but what if I want to analyze one of these triangles here on this sphere? Does this hold anymore? Yeah. And the answer is no, it doesn't really hold. But where does the correction come from? It comes from the metric tensor. And that was the point of driving the metric tensor. We needed a way. All right, so you can think about the metric tensor in our sense as the device to correct for Pythagoras. Okay? For curve space. Okay? And wonderful. We're good. We're good on time. We're doing good. About 2 minutes ahead of schedule. And we're going to move into Christoffel symbols now. So Christoffel symbols, we have to talk about tensors first. And we have say these are tensors. And remember that note that I stopped and paused and I said to you guys that tensors are special to us in general relativity because they have certain properties that we like. They are fixed in frames, which we need. We need certain observers to agree, right? So that's what this little guy is supposed to tell us here. But there's a problem that arises with tensors, and it comes with derivatives. And the derivatives of tensors don't necessarily transform between frames of reference. So we need a device now to correct for derivatives. And we're gonna go through why a derivative, an ordinary derivative, doesn't work, and this new notion that we're about to step upon. So let this tensor equal a derivative of a vector, any x frame. So let this be true, that this tensor equals a derivative of a vector. This is a vector. Okay? Now the question is if this is true and we assume this to be true, what happens when we want to talk about this same tensor in the y frame? Is it just the ordinary derivative? Y frame. Is it just the ordinary derivative? Is this true? We need to figure this out. That's what we're going to do next. We're going to figure out if this is true or not. So, consider equation 5. This is equation 5. I don't even have to write it. That's nice. I kept it up there for a reason. I did that on purpose. And what we're going to do now is we're going to plug, I'm going to call this star. We're going to plug star into 5. Okay? So let's do this. And remember, we're plugging in star, so that means that when we come upon this last part, this is going to be the vector where M is R and S is N. Okay. Let me double check I got that right. Sorry, this is an X. In the X frame. Cool. Now what you'll notice if you are smarter than me, you'll notice that this is the inverse. This could be looked at as the inverse of the chain rule, so we can contract this statement because we have a partial and a partial excess. So let's contract this and let's see what we have. You might recognize that term because it kind of looks like this one, the second part, right? The second part of that term. So we need to put some stars around this because we need to know some stuff about it. I'm not going to circle it because these are different.
We don't need the S anymore.
You're right. Actually, I dropped the sum. Sorry. I said I was going to start dropping sums, so I'm going to stick to my word. Thanks, Dr. Richter. All right, so the question is that we have, from our equation 5, the covariant transformation, we derived a new equation for Tm and y, the tensor in the y frame. The question is this representation of Tm and y the same as this representation? Are these two equal? Right? Are these two equal? And we are going to analyze this part. Two representations. We're going to analyze this one. Okay? So let's write that up here. And also, all right, let me just rewrite this here. Partial v, partial mn, yn, y frame, equal partial xr, partial vr, partial yn. So partial vr, partial y, and x frame. Is this equal to this? This equal to this, right? So I said it, I didn't write it, but now I wrote it and I'm saying it. Two things. So are these two equal? And we're going to use 5, and we're going to remember that this is a tensor term, right? But remember what I went on, and I was like, tensors are combinations of vectors, right? So if we drop one of these indices, we now have a vector, a tensor, a rank 1 tensor, right? So what I'm going to do is I'm going to drop one of these indices. I'm going to drop the s, because that's the second one. Why not? Let's do that. And let's rewrite this one. Make sure I get this right here. Okay, so I'm going to drop one of the indices and we're going to write this here. So we're going to have partial yn partial xr, partial ym, and then remember I dropped one of them, so now this is a vector r x. All I did was write this in this way, okay? So now we can look at our new representation for v m partial y n. And what is this right here? Well, this is a differentiation of a product. So we need the product rule, right? So let's go ahead and do this. We have derivative of the first. Actually, let's do this. We'll do the first term times the derivative of the second term plus the derivative of the first term times the second term. So what we've just stumbled upon now is the reason ordinary derivatives don't work in tensors. Notice that this is the same term as this. Those are the same term. And this is also the ordinary derivative. I'll just put something like that. I'll just put d for derivative. And this term that popped out is our Christoffel symbol for this. So what popped out was an ordinary derivative and a Christoffel symbol, which was the correction for the derivative for tensors. And so we have found our Christoffel symbol, and we've also found our new concept, which is the covariant derivative. So let me erase some stuff and I can write this out. So what we found was Tmn, which we let be a derivative of a vector, right? That was the whole assumption in the beginning. That is equal to the covariant derivative, noted like this. And I did put an m in right here. V, m, is that up or down? And we have the ordinary derivative, this term, plus our Christoffel symbol that we know and love and found just a moment ago. What's that? Rx. This should have a frame too. It should be. I believe this is the y. Okay. So we have now derived equation number 6 if you pull out that equation sheet that I gave you. We have equation number 6 now. Okay. But remember, that was for vectors. That was derivatives for vectors. We found a derivative for a vector. So now we need to naturally ask, what about covariant derivatives for tensors? Right? That seems natural. So what we're going to do now is we're going to expand 6 for tensors. And remember what a tensor is. It's two vectors, or for our case, a combination of vectors. And I use P here. And we have the ordinary derivative of the tensor. Same. See how these are all the same? And then we have our one Christoffel symbol plus, because this is a combination of vectors, and for our case, because we're beginners, we use two vectors, we need another Christoffel symbol. And there's some indices that I'm just going to copy down real quick. And now if you look at your sheet, we've just derived the equation number 7 that we needed. Alright. Alright, so back to what we were doing. We found equation 7, which was the ordinary derivative, and because we had two vectors, we had two Christoffel symbols. So one might be inclined to ask, well, why not? This is what mathematicians do. What is the covariant derivative of the metric tensor? The metric tensor that we ran into earlier. And something that we should understand is that, what do you think the covariant derivative of the metric tensor for flat space is? Anybody? It's 0. It's 0. That's right. It's 0. But if we perhaps want to write this out, this will give us something that I think you will enjoy, because it is indeed in our book, and I will be gladly to show you. So I'm going to do some copying real quick. All I'm doing is copying this for the metric tensor. So I'm literally doing G where there's a T. Mn partial YP partial Christoffel symbol PM R. This is GRN plus RPM N. This one's N. This one's M. GMR. Now, Einstein, I'm not going to speak for Einstein, but I'm sure when he came upon this, he had tons of friends in the mathematical community, and he had to go, I'm not speaking for him, but I guarantee he probably went to a couple mathematicians and was like, hey, help me out here. So he went to the mathematicians, maybe, and the mathematicians would come back, and we would believe them because we're physicists, and that's what we do. Well, we're physicists. And he would say that this gives us a representation to understand the Christoffel symbol. We can now understand truly what the Christoffel symbol is. Let me write down what the mathematicians would come back, and hold your breath, or don't hold your breath, because this is going to be, I'm just going to copy this out, and you can find this as equation number 8. And this is actually in your book. Go ahead and flip through that pages that I gave you. One of those has that exact same equation, number 8, with the indices changed. Right there. So that is truly what the Christoffel symbol is. Let me write it down for justice. Y'all still hold your breath?
Told us not to.
Alright. GBC partial X D. Sorry for the sloppiness, but you'll get the gist that that is what the metric tensor is. And to note what the metric tensor is, we should notice that right away that the metric tensor is a combination of, not the metric tensor, the Christoffel symbol is a combination of metric tensors and derivatives of metric tensors. That's something we should note. Okay, and we should talk about what the Christoffel symbol is and what it isn't. It's not a tensor. Okay? And it is a correction term for us. Correction term for derivatives. It is 0 in flat space. It's not 0 in curved space. And you might ask, Charles, why is this important? Because I don't see any Christoffel symbols up in here. Not a drop. And I would agree with you. There's no Christoffel symbols outright. But deep buried in where we're going to go next, the Ricci tensor, we're going to find some Christoffel symbols, and that's the point of doing all this. And now we're going to move right along, right on schedule, into curvature, where we're going to talk about the Riemann tensor and the Ricci tensor and the curvature scalar. Let's erase some stuff, clean our board up. This chalk likes to stay behind, doesn't it? Are these my fingerprints? Yeah, stop touching the board. Dirty. Anyway, we need to talk about something that we have already heard about, and it's called parallel transport. We're going to transport a vector around this. Okay? And the point of this is we want to find the measure of curvature. So consider a cone where I cut down the middle. And I redraw this cone for you, and I believe it'll look like something like that, right? Where this line is this line if we cut it and put it back together, okay? So let's say we have a vector, and we're going to parallel transport this bad boy over to here. So we're going to go bam, 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 and it's going to come out right there. And we're going to say, there's something fishy going on. Because this, it should have been this one. Remember, these are the same line. So it didn't change in length. The vector didn't change, but it changed in angle. And we note this as, we can say this is theta because I was using phi for sea temperature. And we note this as the measure of curvature. Okay? And this notion is going to come into play here in a minute. Now we have to take kind of a side step, and I have to do a quick proof for you. And we're going to talk about commutators for like 5 seconds. More than 5 seconds, but bear with me. Everyone knows and loves the commutator. And why do we love the commutator? Well, it's because things don't always commute, right? We could have numbers. Sure, this could be 2 and 5, and 10 minus 10 is 0. You know, that's fine. But what if these are matrices or something different? They don't always commute. So this doesn't always equal 0. And that's why we like it. And that's why we use it for a lot of things. Maybe that's not the exact reason, but for my case it is. So I'm going to do, let's consider this commutator. And I'm going to go ahead and just tell you what it is, and then I'll prove it to you. Okay, that's what it is, and let's go ahead and do a quick proof. And we're going to have AB minus BA, so let's just do it down here. That way it's better. A, that's partial x, B, that's f of x. To do a commutator, we're going to need to introduce something, so I'm just going to call this something V, so we can continue. Minus B, f of x, A, partial of x, V. Now if we go ahead and do this, we know this is the product rule. We need the product rule here. This is going to be, let's do I know how this is going to turn out, so I'm going to write this as the first one, derivative of the second. And then we need to add the derivative of the first one times the second. I can't remember which one this came from. Derivative of the first, second, and then we take this last term. I did it right. That feels good. It's good when you did it right. So we have some terms that are going to cancel, correct? And notice that we introduced the V, so we can take it out now. And that's the end of our proof. Okay? I like this square box. I think that's fun to do. Alright, so that's our quick little side proof, and I hope you guys got a little bit of a break from that, because now we're going to have to turn up. We're going to have to turn up, and we're going to have some fun though. It's going to be great. Let me clear this off. Alright, so now I need you to consider two coordinate systems. And I'm going to call this dx mu I'm going to call this x mu and x nu. And the distance of this is dx mu, and the distance of this is dx nu. Now you might notice that we're using, it's exciting, we're using mu's and nu's now. Because we were in M&M's because we're beginners, and now we're moving on to the big boy stuff, and it makes me happy. Alright, so what I'm going to do with this coordinate system is I'm going to make a parallelogram. That could be drawn better. That'll be good. Where this length here is dx mu. And this length here is dx nu. And what we're going to do is we're going to parallel transport around starting at A. Okay? We're going to go from A to B to C to D, and then we're going to come back to A, but I'm going to call A prime. Because we don't know if this is a flat surface. Okay? Seems reasonable enough. So what I'm going to ask you to do now is consider two paths. Okay? I want you to consider two paths. The first path, I'm going to take a vector, the vector at C, minus the vector at D. Okay? And I'm going to subtract from it the vector at B minus the vector at A. Nothing fishy going on here. Right? That's just, there's minus and stuff. That's easy. Okay, but what are we doing here? What is this? You know? Well, if we think about it, this is the difference in the differences of the dx mu's. Remember, I said this might not be flat space. And in flat space, this dx mu would equal this dx mu. But what if that's not true? What if this doesn't equal 0? So this is actually the difference in the dx mu's. I'm going to use the same argument for the vectors on the other side, where I go VC, VB, minus VD minus VA prime. Okay, and again, what is this? This is the difference in differences of the length dx nu. Okay, so what I'm going to do, bear with me, is I'm going to subtract these. Let's say I want to know the difference in the differences. Okay? And what I'm going to call that, for our case, is just dV. So let's write this out. What do we have? We have VC minus VD minus VB plus VA minus VC plus VB plus VD. 3 minuses give us a minus VA prime. And we can notice, this feels good. Crossing off terms is nice. VC's go away. Our VDs, they go away too. And look at that. And what we have left is VA minus VA prime. And we stop for a sec, and we're like, you know what? This is actually what we would expect, right? Remember our cone, when we were around our cone, when it came back to the end, it was the difference between where we started. So this is what we would expect, right? In the difference in differences. VA minus VA prime. So, that's all well and good. But we need to do more with this now. And what I'm going to ask you to do now look again. look again at what this term is. Okay? And notice that this is the change in a vector along a certain distance. The change in something along a certain distance. What does that remind you of? From way in the beginning when we first started? Nah. It was a good guess. Equation number 1, right? The gradient. We had a change in the temperature, or not the temperature, but the sea level multiplied by the length of something, right? Now we have the change in a vector multiplied, or in reference to a length. So now what we have is, this is actually the change in the vector with respect to x mu, right, multiplied by dx mu. That's the length. Sure. But remember, what we found is that we can't take regular derivatives of vectors. So what we need here is the covariant derivative. So to be more proper, this, I don't know why I did that. That doesn't mean, okay, that'll be good. Covariant derivative, mu, right? Sure, that makes sense. Now, consider this again. Vector at C minus vector at D, vector at B minus vector at A. Okay, so we know what this is. That's the change in the vector along the distance dx mu. But what is this? We're going to use the same argument. This is the change in a vector, VA, along dx mu, but how far away are these two paths? This path, this path. How far away are they? Dx mu. Using the same argument, we have that. And what we're going to do now is we're going to do the same thing for our other path, VC minus VB minus VD minus VA prime. And this is just going to be this backwards, right? So I'm just going to write that to save some time. I'm jumping fast. Good. That's good. That V out here is going to take the place for all that. Mu. And remember what we did? We took this minus this, and we got dV, which was equal to VA minus VA prime, which is now equal to this minus this. And I'm going to write that over here. Jay, could you take a look for me? Okay. So what we're doing is we're taking the difference in the differences, VA minus VA prime, and we now have these new representations in terms of covariant derivatives and the gradient that we saw in the beginning. Let's rewrite this dV up here. We have dx mu, covariant derivative mu, dx mu, v minus covariant derivative mu, dx mu, covariant derivative mu, dx mu, v. Okay? Now, what I'm going to do now is arrange some terms, and we're going to make this look a little bit pretty, and we can also pull some things out, right? We can pull out the dx mu's and the dx mu's, because these are partial derivatives, and everybody knows, well, we know, being professionals, that partials in different order come to the same. So we can pull these out. Let's do covariant derivative mu minus covariant derivative mu, covariant derivative mu. Voila! What does that look like to you? Just the term in the parentheses, sorry. Yes, commutator, good job. Alright, so what we're going to do is we're going to analyze this. Right, let's take a look at what this is. We know it's the commutator, but what does it do? What's going on here? Well, remember the proof that I gave you a moment ago that I erased? Maybe we should go back and write that down just so we have something to call upon here. So I'll go over here. Right? And I prove that to you. Okay. So now let's use that proof in a minute. But let's do something first. And I want you to remember equation 6. Can you pull out equation 6 for me? And remember that the covariant derivative of a vector is the ordinary vector derivative plus the Christoffel symbol. But what if we didn't have a vector there? And what if we were just talking about a covariant derivative in terms? So I'm going to use 6 to write a new representation that we are going to need. I'm going to take mu just for kicks and giggles because we're going to use it. Right? So everybody can see how I got that from equation 6 without a vector on it. So we're going to use this now. And remember, it's this times this times this. So let's use 6 and let's write mu. Well, we already have mu written out there. I'm going to do one more thing. I'm going to make this for shorthand because we're cooking. We got to start cooking. We got to go. So we're going to make this partial mu plus Christoffel symbol mu times partial mu plus Christoffel symbol mu, and this is minus partial mu plus Christoffel symbol mu partial mu plus Christoffel symbol mu. Right, and let's distribute these terms. And I want to do this in a special order because I know how this is going to turn out. So I'm going to do this and this one first. Sorry if you can't see me over there. And then I want to do this one and this one. And then the last two. Right? And then we want to minus, we want to do it again over here. This one, this one. Plus, I want to align these because I think you're going to see what we're about to do. We're getting ready to use the commutator again. So I'm going to do this and this. Christoffel symbol. I'm going to do partial mu, Christoffel symbol mu, plus Christoffel symbol mu, partial mu, plus, boom. Look at that. That is beautiful. Now, what we can see right off the bat is that these terms, they go to 0. Right? Because partials, doesn't matter what order we do them in. These terms, this is the commutator, right, of, actually it's the negative commutator, if we think about it, of this one. Partial mu, Christoffel symbol, mu. And then we have another commutator, these ones, this is a commutator, and this is a commutator. So let's write these out real quick. Boom, Christoffel symbols and partials commutator. Okay, now we're going to use the proof that I did to rewrite these commutators, just like that. And we're running out of time, so I'm going to copy this down, just like this. So I'm writing this equation like this. Partial Christoffel symbol, partial x mu plus partial x mu, partial x mu plus the Christoffel symbol. And like I promised, we have now come upon the Riemann tensor. This is the Riemann tensor. But for our purposes, it's the Ricci tensor. So if we go back to our dv, this right here, let's write that over here. dv dx mu dx mu. And we have v, and then I'm going to use r mu mu because that's what it looks like in the field equation. All right, and then from that, I promised that I'd tell you how to get the curvature scalar. So remember with vectors that we can do an inner product that'll give us something to the real numbers, right, and give us a scalar. So similarly, I'm not saying that's exactly how you use the Ricci tensor. For our purposes, it's the Ricci tensor to get the curvature scalar, but similar things can be done to do that. We don't have time to do that. We have, I'm going to finish up here. Okay, so we're going to do a quick review. What have we come upon? Well, we found the Ricci tensor, right? And what was the Ricci tensor? Well, it was made of Christoffel symbols and derivatives of Christoffel symbols. But what was a Christoffel symbol? Well, if you can recall from your book, that was the metric tensor and derivatives of metric tensors, right? And then what was the metric tensor? Well, if you recall, that was the device that we used to correct Pythagoras, right? Cool. So hopefully you have learned some stuff. We're going to do the stress energy momentum tensor, which is going to take like 3 minutes, and then we're going to conclude, and then I'll take some questions. Okay, stress energy momentum tensor on the right side of Einstein's field equations. Like I said, we don't have time to derive it, so I'm going to explain it in terms of a big O matrices. It's going to be worth drawing these out, so I might as well do it. Just so you guys can see it. Man. Thank you, whoever said that. Okay. So, this is what this term looks like. Now, this term right here, T00, is what is known as the energy, time energy component. Okay? Time energy component. Okay? These terms right here are what's known as the energy flow components. Okay? These terms right here are what is known as the momentum density components. And then these terms right here are literally everything else that we could think of that might affect mass. So this is stress, momentum, pressure, flux, components. Everything that we can embody into mass and energy that we can think of. Now some of these terms are going to repeat themselves. These are not all the same, but why not have more than have less, right? Okay, so real quick, you can think of this as energy per volume, right? Or you can think of this, what is energy? Work, time, distance, right? Or it's work, that's force. Work is force times distance. What is volume? That's length cubed. We can cancel one of these L's. Well, not cancel, but you get the deal. Yeah, cancel. L squared. What is force per area? Pressure. Good. Pressure. And that is very briefly the stress energy momentum tensor. Okay? And now let's do a concluding thoughts here. Okay, so Einstein thought, when he was writing down these equations, he thought, okay, I need something that accounts for everything that could happen to mass, right? And I also need something that accounts for curvature. And naturally, he was like, well, that's the Riemann tensor, because that has pretty much everything to do with curvature in it. So he was like, I bet you that the field equation is this. He was like, money down, hands down, that's it. And then he found something. And because of energy conservation, when we take the covariant derivative of the right side, well, this is 0. But he found something now. He found something. He said, what's the covariant derivative of the Riemann tensor? Well, that isn't 0. But what he did find was that it was that. And he said, oh dang, check this out. Guess what? That does equal 0. We have the left and we have the right side. We're almost there now, right? We're almost there. He found something else. He found that for dimensional purposes, he needed the speed of light to the 4th underneath here. Remember G? Sure. But he was missing something, and there's a really cool story behind this, the cosmological constant. He was working on this before he even found the field equations. He knew about the constant before the field equations, and people were like, nah, man, that's garbage. That ain't nothing. And he was like, you know what? Remember another thing, that the covariant derivative of the metric tensor is 0 in flat space, right? So when we're in flat space, we want our equation to fall to our lovely Newton equation. So he said, this is it. I've now found it. And it turns out this term here is actually really small. And we actually don't include it often because it's so small unless we talk about things like black holes, galaxies, things that are really big. And that is the Einstein's field equations. Thanks.